guys, this is the video makeup lecture for our second day in the iterated integral section in Stewart. Last class we introduced what the double integral was. Just wanted to give you guys a little bit extra practice working with double integrals today and let you guys see some harder examples. So let's go ahead and get started with that. First off, before we really get going, I want to recall where we left off. We introduced the double integral of a function over a given xy region. So you specify some sort of rectangular region of input variables here for this function, and if you wanted, we could find signed volume between the surface generated by that function and the xy plane in R3. So what I mean by signed volume, if you've got area that's above the xy plane, it counts as positive, and if it's below, it counts as negative. Now, a comment before we really get rolling here. Let me make sure that I can actually draw this thing appropriately. Go ahead and recall that my notation here for my double integral, there are a couple different ways we could write this. First off, if I just wanted to vaguely refer to my region, we could go ahead and leave just R denoting my region of integration for my integral here. If I happen to know my region, if I know R equals, there are a couple different ways we could specify rectangles here. Either I could give you a cross section of my x coordinates and my y coordinates, or maybe if I wanted to spell it out slightly differently, say I wanted to specify all points where a was stuck between, or x was stuck between some a and b value, and y was stuck between some sort of c and d value. Both of these notations refer to the same exact rectangle. Okay, I'm specifying some sort of interval of x values and some sort of interval of y values, on which I form a general rectangle. If I know those bits of information, I can actually spell out my bounds a little bit more explicitly, right? We usually didn't lead this in terms of dA. We would usually write dy dx or dx dy. So let's see if we can get a little bit of practice working on that with an example, just to remind ourselves how this worked. Okay, I have got this integral for us to work on. Evaluate the double integral of x plus y squared minus 1 dy dx, where y ranges between minus 2 and 0 and x ranges between 1 and 3. Recall the way that we worked on these is we started from the inside and then we went out. So that meant that in a case like this, if dy appears more towards the middle, you're integrating with respect to y first, and then you're integrating with respect to x last. Now, if I set up my integral in this particular manner, remember whenever you are integrating with respect to a particular variable, even if other variables appear in your expression, whenever you're integrating with respect to a particular variable, that acts like your variable, and everything else just acts like a number. So, in this particular case, I know, my outer integral information here. I'm not really going to end up doing anything with it on this step. We have to worry about anti-deriving with respect to y first. What I'm going to go ahead and get here, if I anti-derive x with respect to y, x acts like a number. If you anti-derive a number with respect to a variable, really all we end up doing is just tack that variable on. Here, my y squared term, I'm anti-deriving with respect to y. That should work totally normally, so I'm just going to get a regular old y cubed over 3 for that term. The minus 1 is also going to work pretty normally. I'm going to go ahead and get a minus y for that term. Now, thing that I'm going to go ahead and note is we have just anti-derived with respect to y. What I need to do is make sure that I get my bounds straight with respect to y next. So I will go ahead and remind myself that I need to evaluate these. Don't forget, whenever I write this evaluation bar, I find it helpful to specify which variable we just anti-derived with respect to, so we can remember what actually needs to get plugged in where here. Okay, we're not plugging stuff into x, we're plugging stuff into y. So if I go ahead and do that, my top bound goes in first. If I substitute 0 in, well, that's 0 all the way across the board. X times 0, 0 cubed over 3 minus 0, etc. That means I just need to subtract what happens when I substitute y equals negative 2 in. Well, that'll give me a minus 2x for my first term, a minus 8 over 3 for my next term, and if I'm subtracting a negative 2, I am really ultimately adding a 2 for that last term. Okay, so once I clean all of this up a little bit, first off, I can distribute some of my minus signs here. I'll go ahead and note this will give me 2x plus 8/3 minus 2. I can clean this up even more if I would like and simplify my constants. You'll note 8/3 minus 2 is the same as 8/3 minus 6/3. This is going to just reduce to 2/3 here. I will scroll down a little bit to give myself some more room. Once I do this, this is a regular single variable calculus problem, right? So we anti-derive totally like normally. Okay, apply my basic power rule and whatnot, and then plug in your bounds like normal. Okay, top value goes in first. Oops, forgot to throw my x on here. Top value goes in first, so plus 2/3 times 3. And then I have to subtract what happens when I plug in my bottom bounds. So this will be basically 1 plus 2/3 here. If I would like to, I can clean some stuff up. This will look like 9 plus 2, so 11 in this first slot. Minus basically 3/3 plus 2/3, so minus 5/3 over here. This is 33/3 minus 5, so 28 over 3 should be my final answer for this particular question. Okay, so the way to interpret that, this function that I initially had, if I scrolled way back up to the top, if I wanted the signed volume over the rectangular region that was prescribed, this is going to be the value for that signed volume. Okay, let's try one more of these, but make it a little bit harder. Okay, I'm going to find the volume under the surface. Z equals 2x plus y quantity cubed over the region R, where I've specified a region R. Here, I'll go ahead and ask, let's see if we can do this where we set up the problem so that we integrate with respect to x first. All right, so first off, this is tricky because I'm having you set up the integral on your own, and then we'll worry about the tricky bits that come along from actually anti-deriving this question. Okay, first off, if I am anti-deriving with respect to x first, well, that means that guy pops up in the middle, so this is going to be a dx dy problem. Second thing that I'm going to note is, since I want my bounds to match up, the way that this notation worked for my r, I have to look at this section here, x is stuck between 0 and 1, to tell me what my bounds on that x integral are. Okay, so here's my 0 and 1. Similarly, my bounds on y were going to be 0 and 2. So now we can go ahead and treat this. Few comments. One, you notice I have a composition of functions. This is sort of like calculus 1 in that when we get those, we still have to fall upon our antiderivative tricks like u substitution and integration by parts and all those other fun things. Just we have to be really careful in cases like this to watch what we're treating like a variable when we do it. Okay, now if you really, really, really wanted to, you could actually cube this out. But I do want you guys to see what a u substitution question is going to look like here. So we'll proceed in that manner, right? We are going to go ahead and try a u sub for this guy. Okay. Usually you pick the inside of your composition, okay, as your u, and since we are going to be anti-deriving with respect to x on this particular pass, well, I'm going to make my du basically picked with my x derived in, or with my u derived in terms of x. So here we're doing dx for my first pass. What I'm going to do is basically take my partial with respect to x of u here to compute my du. So I'm going to go ahead and get 2 dx for that. Another way to think about this is a half du is going to be the exact same thing as dx. Now I'll go ahead and scroll my page down so I have a little bit more space to work here. I'm going to go ahead and work on plugging some of this stuff in. Now, first off, my y integral is a distant thought right now. I'm not going to worry about him. I'm just worrying about this x integral. So if I go ahead and substitute all my stuff in, this is no longer 2x plus y quantity cubed. This is now going to be a u quantity cubed. I no longer have a dx in this problem. We just said that this is going to be the same thing as 1/2 times my du. So, and actually, I'm going to go ahead and make a fast note that these bounds, these actually don't apply to my variable anymore. That 0 and that 1, those were in terms of x. So if I want to fix this guy here, usually before we would say that you could substitute into u. You can still do that, but be careful what you're substituting into u, right? U was a function of x and y here. These were x bounds. So if you wanted to fix the bounds, you could plug that lower bound in for x. We have to leave y blank. You could plug this upper bound in for x. We have to leave my y blank. And we're going to proceed with my integral like that. Okay? So here, if I'm actually anti-deriving, I will get u to the 4th over 4, but it's times a half, so over an 1/8. This is going to be evaluated between, well, remember we were substituting in for u here. We're evaluating this between u of 0 y and u of 1 y, whatever that is. Usually though, most of you guys tend to not evaluate u substitutions by replacing your bounds. The more common method that I've seen people do is they revert back to the original variable, so I'm happy to go ahead and do that here. If I'm doing that, first off, I can go ahead and replace my u. This is supposed to be basically 2x plus y quantity raised to the 4th all over 8. And my original x bounds were supposed to be between 0 and 1. So I'll scroll down and give myself a little bit more room here. I can actually plug those things in, right? So this will now leave me with, if I substitute stuff into the top here, I will get 2 plus y raised to the 4th over 8. And then if I subtract what happens when I plug in the bottom, this is going to be y to the 4th over 8. Okay, and at this point, this is going to be a regular calculus 1 integral. We're now in terms of just one variable. It's still another chain rule problem, or sorry, not chain rule, but u substitution problem. But since this is calculus 1 territory, I'll basically leave it at that. You guys should be down pat with your calculus 1 stuff now that we've gotten rid of our other variable in this particular example, right? So basically this is going to be another u substitution with u equals y plus 2 in my first integral. We are probably going to want to split this up into two pieces, because the second part doesn't require u substitution, right? So we can tackle this using old methods. We've got the Calc 3 part out of the way. Now, I mentioned to you guys I did want to show some, more sophisticated techniques, so stuff like u substitution as it applies in higher dimensions. What other kind of techniques do we have for evaluating some of these integrals? Well, I'll go ahead and skip over to my next slide here. We'll look at Fubini's theorem. Here, what this theorem states, if we've got a continuous function on a rectangular region, then what I can do to rewrite the double integral over that region is, if I want to integrate with respect to y then x, or if I want to integrate with respect to x then y, it doesn't matter. I'm going to get the same result both times. Now, you may have noted in that previous example that we just worked on, but didn't quite finish, I specified for you guys an order of integration that had us dealing with x first and then tackling y. That was actually totally unnecessary. If you had really wanted to do y first and then x, we would have been completely in the clear, and that would have been an acceptable alternative option because we had a continuous function. The only thing that you have to do is make sure that whenever you select your bounds, to integrate here, they have to match up with the appropriate variable, right? So your x bounds have to go with x, your y bounds have to go with y. As long as they line up, the order of integration doesn't matter. Now, you may notice that I have this guy starred right here. If f of xy is a continuous function, the reason that I have this thing starred is I wanted to make the following observation to you guys, or point out the following thing. This theorem basically also works in a couple other situations. This also works if f is bounded on my region R. So basically, if it doesn't go blowing up towards infinity or anything crazy like that, if you can put a upper and a lower cap on it, this works too. If f is discontinuous only on a finite number of, let me scroll and give myself a couple extra lines here, of smooth curves. So basically what I'm saying is, if you have a break in the middle of your surface, but it looks like a differentiable curve from Calculus 1, if that's the kind of break where you have a discontinuity, we can switch up my order of integration, doesn't matter. Another option is if the iterated integrals exist. So really, the shortcut way to think about this is really anything I would give you guys in this class. Okay, so anything, missing a letter here, you'll see basically in Calc 3. I'm not going to give you guys any ridiculously crazy, stupid stuff that you won't be able to anti-derive, okay? So if you guys see it, we're probably going to be able to switch the order of integration. This can actually come in potentially a little bit handy. Let's see if, actually, I'll hold off on switching at the moment. We'll just play around with a couple basic properties too. I'll give you guys some other tools before we really worry about doing a bunch of crazy examples here. Other tools that you guys have for evaluating these iterated integrals, okay? One of them is going to be that we get a lot of algebraic rules, kind of like we did for single variable calculus. Namely, if you have sums, you can go ahead and split them apart. If you have constants on your function, you can pull them outside of the integral. This last one is more kind of a common sense statement, hopefully. If one function is bigger than the other, your double integral is going to end up larger than the other on the same region. So basically your signed volume should come out larger. So hopefully that's reasonably expectable for us. Okay, let me go ahead and see if I can pull something particularly useful out of this this second case here, because not only do we get these nice algebraic properties, this second rule works in a couple more cases than you maybe might expect that it does. To highlight, we have a trick for if you've got a function of x multiplied by a function of y, and you want to integrate over that region. So if I wanted to test this out, here's kind of my idea, right? We can start writing this. Usually I give you guys some set of bounds that we're integrating over. You know, I would probably write it in this manner rather than using r and dA. I would actually specify you know, dy dx or dx dy. Now, if you wrote this in the totally you know, backward manner that we suggested by Fubini's theorem, either way that you start out, it doesn't necessarily matter too much. If we had wanted to write this as doing my y integration first, we totally could. No matter, doesn't particularly affect the end result here, either way. But if I start out with this particular function, let's say that I scrap the one on the top and I'm just going to work with this one that's on the bottom here. I just said, step 2, last slide, we can pull out constants if we want. Now an observation that I'm going to make is if I'm integrating with respect to the variable x, anything in terms of y is going to be a constant. So even though we're writing this guy in terms of a function, you know, this guy is constant with this dx, you know, variable that we've specified to tell me what I'm integrating against. So what I'm going to go ahead and do is pull this guy out of my dx integral. Okay, what that'll look like is this. My outside integral, I'm not doing anything to mess with it yet, but on this inside integral, I've said that g of y is just a constant that I can go ahead and pull out. So I'll be left with an integral of f of x with respect to x here. Okay. Another comment that I'll go ahead and make that's very, very similar in lines, back in Calculus 1, we should have hopefully learned that this guy here, if you take the definite integral of a function over an interval, this guy is just a constant in general. This isn't necessarily, you know, specifically with respect to dy or anything like that. Just if you antiderive f and then you plug in the bounds, you've gotten rid of all of your variables at that point. You just have a number. So we're going to do the same trick. We can go ahead and pull this out of my dy integral. Now I'll scroll down to give myself a little bit of room here. What that means is I can think of this as basically my f of x integral that I've just pulled out of my g of y integral. Let me make that look a little bit more like the appropriate letter. Okay, so in other words, what this is really telling me, if I wanted to break this down and, you know, give you guys a rule that didn't bother showing all of the work, here, if I have got this f of x, g of y, if I can split my function into, you know, a product of a function of x and a function of y, well, here I can basically set this guy up. Okay, if R is a rectangle, I can set this guy up as my integral of f on my x bounds times my integral of g on my y bounds. Okay, that's what this trick is letting me do. So I'll go ahead and demonstrate with an example here. Let's say that I wanted to take this definite integral right here. We've got the function y, the function cosine x. So this is a product of a function of x and a function of y. My x bounds are from 0 to pi over 2, and my y bounds are from 0 to 4. What that last slide said that I could basically do was, if you want to, and I can really break this down in a similar manner, if I want to, I can go ahead and pull the y out of that x integral, right? So this will look like y times that cosine of x dx integral. Y is a constant with respect to this integral, so sure, it can go ahead and leave. On the other hand, this guy, this full-on definite integral, evaluates to a constant, so I can pull that out of my y integral, right? So I will get this guy here, this trig integral, times whatever happens when I went to evaluate my integral for y. Now, if you were just directly using the formula in the sense that I gave it in the last slide, that I could split this guy up, this definite integral up as f of x g of y, and then break this down as a product of my x integral over my x bounds and my y integral over my y bounds. If you wanted to jump the middle step, you could. The nice thing about this now is just straight up calculus 1 territory, right? We can anti-derive each of these pieces completely separately. Okay, same deal over here, y squared over 2 between 0 and 4. What this means that I'll get here is basically my sine of pi over 2 minus sine of 0 times my 4 squared over 2 minus 0. Well, both of these end up being 0, so they kind of fall out. In this particular case, I can clean this up, just get 1 times 16 over 2, which is 8, and just get 8 back. And notice we didn't have to really keep as much track of, oh, I'm anti-deriving with respect to y, so x needs to be constant, or vice versa. This becomes a calculus 1 problem in this manner. Now, as a side note, I can do this example the other way. Okay, old methods still work. If I wanted to, I could go ahead and, split this guy apart and think about it in terms of performing an x integral and leaving my y alone. If I wanted to treat this function as a function of x, y just acts like a constant, so I hang on to it. This is going to act just like 2 cosine of x or 10 cosine of x. We just carry down the y. If I'm carrying that down as a constant coefficient and I'm anti-deriving cosine gives you the function sine of x. And since we just anti-derived with respect to x, I have to keep track of what my bounds were. Okay? So here, I need to clean that up before I can do my next pass. Of anti-deriving, I'll go ahead and get y sine pi over 2 minus y sine 0. We said before sine of 0 is 0, so that'll drop off. If I want to evaluate sine of pi over 2, that's really just 1. So I'm anti-deriving y dy on 0, 4. This is obviously going to turn into y squared over 2 between 0 and 4, or 16 over 2 minus 0, which we get back the same exact thing. And I'll also go ahead and note, just for completion's sake, you said old methods still work. The other tricks that I introduced to you guys also still work. So I will go ahead and give you guys yet another note that we also get the same answer if you set up your integral with the bound switched, like I mentioned before. Okay, we currently have this set up for dx dy. If I wanted to do dy dx instead, well, we have to match my bounds with my variables here. So if I wanted to reverse the order of integration, let's say I just preferred to get the y out of the way first, we're going to get the same exact thing, right? So just to demonstrate super quickly here, I'll go ahead and scroll down and try this one more time, just to really nail in that this truly does work. We can switch my order if we find it convenient. We're not dealing with the dx integral yet. We need to tackle the dy first. You'll note that x acts like a constant, so cosine x acts like a constant. We're just going to hang on to it. And I derive y because y is your variable here. Okay, we have to evaluate this guy between 0 and 4. If I do this, you'll notice I'll get the same, 16 over 2, so I'll get 8 cosine x, basically minus 0 if I plug that in. So, if I wanted to clean this up, I don't need to worry about the 0 part. I'm just worried about the antiderivative of cosine. I'll get 8 sine of x evaluated between 0 and pi over 2. Well, this is basically going to be 8 times 1 because we've been over this. Sine of pi over 2 is 1. Sine of 0 is 0, so I'm subtracting 0 off. You get the same thing either way, okay? So you have options depending on integrating which variable, which one you would find most comfortable to do first. If you like switching the order, you can. So what I'll go ahead and do here is move on over to my last slide, which this is just going to be a quiz for you guys. Evaluate the double integral of that function on the region R, which again, don't forget, these guys are specifying my x values. These are specifying my y values, okay, of a rectangular region that I want to integrate this on. I'm not telling you guys necessarily what order to set this up in. If you want to do dy dx, if you want to do dx dy, or if you want to set it up as one of those and then rewrite it as a product of single variable integrals, you have choices here, okay? So I'll take this, again, kind of my usual quiz policy, at your earliest convenience, although sooner will significantly be better than later. If you guys have any questions, please feel free to let me know.